Greetings. This is a very interesting problem where argon is inside the cylinder piston arrangement. Now, um, the interesting point with this problem is that we use all the different laws of thermodynamics plus the availability equation. And there's another interesting point in it where we first defined initial and final conditions and we calculate the process. Then we define the process and return to calculate the final properties. So there are two different points. Let's start with the problem. Now, the problem tells us that argon is inside the cylinder piston device. Now, initial temperature T1 equals 400 Kelvin and P1 equals 350 kilopascal. And V1 initial volume is 0.01 cubic meters. Now, there is a furnace where T of furnace, the furnace temperature is 1200 Kelvin. And this furnace transfers heat to this cylinder piston device. Basically, it transfers heat to argon. Now, it tells us that the process that happens is isobaric. Isobaric process, which means that P2 would equal P1 would equal P, which is 350 kilopascal. Now, the final condition, as the heat transfer continues, the final condition V2 equals twice V1. That's the final condition. V2 equals twice V1, which would be 0.02 cubic meters. We also know ambient conditions. Ambient conditions T0 equals 300 Kelvin and P0 equals 100 kilopascal. The ambient pressure is different from the argon pressure inside this cylinder piston device. That means that perhaps the piston basically exerts pressure on argon. Okay, now what does the problem ask from us? First, it asks us the useful work output. The useful work output. B, it asks us the exergy destroyed. And C, which is a very interesting point, maximum possible work during the process. Please note that in the first two cases, we have basically defined initial and final conditions, and we are asking about process parameters, work, destroyed exergy. But In the third case, we're moving differently. We are defining the process. We say, assume a process where maximum work is possible to produce. And once we define the process, then you would move to calculate final properties and other process parameters. Now, this is a different aspect which we shall follow it right now. Even before we start to solve the problem, we could draw it on a diagram, and this would be quite informative. Look, there are two diagrams which I select. One is the TS diagram, and the other is PV diagram. Now, it's a constant pressure process, so the PV diagram would just look like this. This is V1, and this is V2, and V2 equals twice V1. This is our process. This is point 1, and this is point 2. Now, as for the TS diagram, there is a constant pressure line on the diagram. And if this is the constant pressure line on the diagram, which usually looks like this is the P equals 350 kilopascal line. And well, certainly the temperature increases, you're heating argon, so certainly there would be some increase in temperature, and also there would be some increase in entropy. So this would be point 1, and the process goes to somewhere like point 2, and this would be T2, and this would be T1. We know that T1 is 400 Kelvin. For T2, we don't know what it is. Our next step is to learn the properties. Well, Argon properties are in all thermodynamic tables. They usually give it in every book, and I will just repeat it here. For argon, critical temperature, T critical is 151 Kelvin, and P critical is 4.86 megapascal. Look, T critical is 151, and our temperature is 400 Kelvin. So basically, we are 3 times the critical temperature. And as for critical pressure, this is 4 megapascals, and this is 350 kilopascals in scale of about 1 to 10. This means that the pressure is far lower than the critical pressure. Temperature is higher than critical temperature, so a perfect gas assumption would be good. And so we may also read other properties. R equals 0.2081 kilojoules per kilogram Kelvin. CP0 equals 0.5203 kilojoules per kilogram Kelvin, and CV0 equals 0.3122, again kilojoules per kilogram Kelvin. And finally, gamma, which is the ratio with CP0 and CV0, is 1.667. These are argon properties that we have read from the table. Once we know all temperature, pressure, and volume properties at the start of the process, we can also calculate the mass or the mass of argon inside the cylinder. Well, the perfect gas law tells us that P1V1 equals M1 or T1, and therefore M1 equals P1V1 over RT1. We have all the values on the right hand side. Therefore, M1 equals 350 times 0.01 divided by 0.2081 times 400. And the outcome for mass is 0.042 kilogram. Once the perfect gas law applies, it both applies for the initial condition and the final condition. So the final condition, pressure is the same, but the volume has doubled. Therefore, P2V2 equals MRT2, and therefore T2 equals P2V2 over MR. And therefore T2 equals 350 times V2, which is 0.02, and divided by 0.042 times 0.2081. And the outcome for T2 equals 800 Kelvin. Well, the volume has doubled, the temperature has doubled. The rest are the same. We could write it in this way: MR between points 1 and 2, P1 V1 over T1 equals P2 V2 over T2. Pressures are the same, volume has doubled, temperature has doubled. And that's the knowledge we can gain from properties. We don't need the only knowledge that we have used for the process is that it's a constant pressure process and nothing else. Now, our next step is to simplify the governing equations. These are all the equations: the mass conservation, first law of thermodynamics, second law of thermodynamics, and the availability equations. Now, for the present problem, since there is no mass entering or leaving our cylinder piston arrangement, then our governing equations would not have these terms. Mi and me are zero, and therefore all its relevant terms in different equations would all be zero. Now, we have to integrate the left-hand side for the initial and final condition, and the rest of the terms, heat transfer, work, and entropy generation would be present in our discussion. Now, let's simplify these equations, and for the mass conservation law, the left-hand side is integrated and remains, so it is M2 minus M1 equals 0. We basically integrated between initial and final conditions. Now, the first law of thermodynamics simplifies to M2U2 minus M1U1, which is our left-hand side integrated between the initial and final conditions, equals, now there is heat transfer, there is no mass coming in and going out, there is only heat transfer, Q12 minus W12. The second law of thermodynamics simplifies to N2S2 minus M1S1 equals Q12 over TP plus Sj. And finally, the availability equation simplifies to M2A2 minus M1A1, and that equals, there's no mass entering or leaving. These two terms vanish. We are only left with the rest of other terms, which are 1 minus T0 over TB times Q12 minus W12 minus P0 times V2 minus V1 and minus T0S jet. Well, although it looks fairly straightforward, but still you have to make some comments on the way we have simplified this equation. You see, the first thing we shall do for any simplification of the equations is to decide what are we simplifying these equations for. And you see, for these equations, the boundary I select is this one. There is no heat transfer from this boundary. The only remaining boundary that I have to take is a selection, which I shall do now and then shall discuss it further very shortly. You see, I would select the boundary here, this very boundary where heat transfer happens through it. I would take it as the furthest boundary, and here the temperature is 1200 Kelvin. So my selection of the boundary for these three boundaries is a boundary where there is no heat transfer from it, but this boundary is a boundary where its temperature is 1200 Kelvin, and therefore it equals the furnace temperature. This boundary is a boundary where work happens through it. So this boundary moves, it moves the piston, and therefore it does work. Now, this boundary is a boundary where heat transfer happens from it, and its temperature is 1200 K. Now, you see, this is the work. The work is the cylinder piston work, and this is its boundary. What's the pressure of that boundary? Its pressure is 350 kilopascal. The selection of the boundary is very important for work. This boundary has a pressure of 350 kilopascal. It does work on the piston. And therefore its pressure is 350 kilopascal. This boundary, its temperature is 1200 Kelvin, and heat transfer from it. Basically, the irreversibility for heat transfer between 1200 Kelvin and the temperature in the argon temperature, which is initially 400 and finally 800, are lower than 1200 Kelvin, all the irreversibility here is included inside our boundary. So if this boundary is TB, which is 1200 and relates to the heat transfer, and also all the entropy generation is included inside this boundary. I shall try to solve the rest of this problem, put numbers to all these equations in the next video. Thanks for watching and cheers.